Hello everyone, welcome. This is Dr. Rhonda Kofelt, and I am going to do a discussion on Chapter 17 of our TRO textbook, Aqueous Ionic Equilibrium. This will be part one of that. These are the outcomes of everything that we're going to do in Chapter 17, and there are 5 parts to this. I try to cut them up into small chunks so that you have time to work on each of these concept areas as we go. Part 1, we're going to be talking about buffer solutions. If you were with me for the previous chapter, we were talking about general acids and bases and things, characteristics of those, and now we're doing the buffers. And buffers are, as we're going to find out, things that are going to resist changes in pH when you add acids or a base to it. So the first calculations we're going to do, in addition to looking at the general characteristics of buffers and how you do them, is how to use an ice table, and then how to use the Henderson-Hasselbalch equation in order to calculate the pH of a buffer solution. So, as I said, buffer solutions are those that resist a change in pH if you add acid or base to them. And so the way it works is that the buffer contains 2 components. It's typically a weak acid and then the salt of that. And it could neutralize the acid if you add acid, or it could neutralize the base if you add the base. And so in order to do that, they must have the weak acid and conjugate base, or a weak base and its conjugate acid. And so another way of saying that is the salt of the weak acid is its conjugate base. So an example is you see in the blood, in the human body bloodstream. Blood is a mixture of carbonic acid and bicarbonate ions, and so I call it the salt of that because typically for the bicarbonate to be put into the solution, it's going to be in some soluble salt compound like sodium bicarbonate. All right, and so when you put those 2 things together, you've got the bicarbonate, which can accept a hydrogen, and you've got the carbonic acid, which can donate a hydrogen, or also known as proton, right? And so they can act as either an acid or a base. So when I make those in the lab, and in biochemistry especially, we use buffers, and you also use them in manufacturing if you want to keep or maintain a pH at a certain level. An acidic buffer is going to have a lot of weak acid and conjugate base, and so you're going to pour those together, as I said, usually the salt of whatever your acid is. So your example here, if you look, is the conjugate base is going to be the sodium salt of the acetic acid. So you've got the acetic acid that you're putting in there, and then sodium acetate, so that you can get the acetate ion into solution. The sodium is a bystander. Okay, so it's just going to be, it's just to get that in there. And so a lot of times when we are setting up our ice table and all that, we just ignore the sodium because it just kind of hangs out and it really doesn't change anything, do anything, adjust equilibrium. It was there as like a carrier to get that acetate ion into the solution. So if I have a buffer set up and I add a small amount of strong base, the base will be neutralized by the weak acid. So if I have the sodium hydroxide in this case, I have acetic acid in here. The acetic acid, when combined with those, will form water and sodium acetate. And the pH won't change very much. Okay, because it really keeps it. Remember, if it's going to become basic, it's going to have free OH minus in the solution. And so what this does is it scavenges those OHs and makes sure that it adds it to the H's, and then so you got H's here and you got OHs there, and they form water. Okay, so the pH doesn't change very much. If you don't have a buffer in there, the pH would change a lot. So if you add a strong acid to that solution, the acid will be neutralized by the conjugate base. So it will be neutralized by the sodium salt, because this is actually going to be in that form, and the H can add to this right here area and form the acid, and then you'll have sodium and chloride left over, which will just form a soluble salt in the solution. So again, it's not going to do a whole lot as far as the reaction goes. So when we have an acidic buffer, we add base to it, then the weak acid is going to react with the added base and neutralize it. And so your H3O plus and your OH minus are basically combining to make water, which keeps the free H3O plus out of solution. So as long as you don't have free H3O plus floating around in the solution, it's not going to be acidic, because remember, the pH is going to rely on what the H3O plus concentration is. Addition of the acid to an acidic buffer, you're going to have the conjugate base grab a hold of that H plus and turn it into the molecular form, which again keeps your H3O plus from being free. So the key is to sort of bind up the OH minus or the H3O plus, depending on what you're adding to the solution, to keep it from being freely in solution, because that's what makes the pH change, if you have OHs or H3O pluses in solution. So when we make an aqueous solution, we see something that's very interesting called the common ion effect. And the common ion effect is what gives these buffers this characteristic to resist changes in pH when you add more acid or base to them. And so if you have, I know it's hard to see, it's kind of cut off here, but this is just a 0.1 molar acid solution, okay? And its pH is 2.90. A 0.1 molar sodium acetate, I think is what that is, would actually be 8.90, because it's just the sodium salt. It doesn't have that extra H to donate. If you have both of them, 0.1 molar of each solution, the pH is somewhere in between those, because the acid is there to have it on the low side, but that salt is there to keep it from going all the way down to the 2.9. And so that's the benefit of this, because if you don't want that pH to go too low, then you're going to have to buffer it. All right, so when we're making a buffer solution, we calculate what the pH of that is, because you're going to make these up at certain pH ranges. Practical example of this is in the plating industry, for example, or when you're trying to separate metals out. Different metals will precipitate out of a reaction at certain pHs. So you want to buffer that pH so that it stays around 6 if that's the one that you're trying to precipitate zinc out. And all the other metals will stay in solution, but zinc will precipitate out. And if your buffer's in there keeping it at a pH of 6, you can get all the zinc out, right, before the pH changes. And then you can pump that off, pump the zinc off the bottom, and you've separated the zinc out of there. So there's a lot of, especially when you're separating metals from metallic solutions, this is very handy. All right, so we're calculating the pH of a buffer solution. That's 0.1 molar acetic acid and 0.1 molar sodium acetate. All right, so you're going to have to know what the Ka is for these. And if it's not on your problem, you know you can look that up. And I'll tell you that the Ka for this reaction is 1.8 times 10 to the minus 5. So, I mean, I looked it up. So, you can look it up when you're working your problems too. After a while, you'll kind of get used to it. Like you're going to see acetic acid a lot. And so Ka for that is 1.8 times 10 to the minus 5. All right. So we know that the Ka for any reaction is going to be A minus times your H plus divided by the acid, right? We learned that in the last chapter. So I'm going to look at my ice table over here, and I have everything's a 1-to-1. So they're all going to be in a 1-to-1 ratio. So I have this time, notice I'm not starting with 0. I'm starting with 0.1 for my acetate ion. Notice the sodium is not written on here because it's a spectator and it doesn't have anything to do with the reaction. So I'm just leaving that out and writing it as the acetate ion itself. All right, so I have acetic acid and I have acetate, and I'm putting it in water, and then I'm going to be producing some H plus. So the change is I'm going to go down X in my reactant and up X in my product, and so this will be minus X, 0.1 plus X. Okay, so this is a little bit different. These buffers already have part of the product added in there before you even start. Okay, so you can kind of see, if you think back to Le Chatelier, how that would kind of resist that forward reaction. All right, so since I have concentrations for these things, I can go ahead and I can solve this. So Ka, which is equal to 1.8 times 10 to the minus 5, is equal to my H3O plus is X, because I don't know what that's going to be because that's what's happening, times the 0.1. And notice that what I'm doing is I'm using approximation for this when I do my calculation, right? So then that's going to be divided by 0.1, all right, because I'm using approximation. Otherwise, those would be minus X and minus X, or plus X, but I don't have to do that, all right? So 1.8 times 10 to the minus 5, since those cancel each other, is X. So that is the concentration of my H3O plus. So the pH, which is what it's asking me for, is the negative log of the Ka. So the pH is going to be 4.74. So that's my buffer solution that I've made up before I do anything to it. Okay, so that's calculating the pH of a buffer solution. I've got a couple for you to practice on here. If you're in my class, you have a workbook and it's got answers to these, and so you can make sure that you're working them correctly. Okay, so we've been doing things with the ice table, and an ice table is fine, and if some people continue using the ice table, they just have to look up the Ka or whatever. That's fine, but Henderson-Hasselbalch is a work saver, and it is like Dr. Kofeld's easy way to work these problems. And so I think I'm gonna work the first one, showing you both ways with the problem, and show you how the Henderson-Hasselbalch equation is your friend. So pH is equal to pKa plus the log of the base over the acid, and this is either, depending on which one you're looking at, conjugate, right? So the Ka this is derived from your Ka expression, okay? And it allows us to do the pH of the buffer without having to figure out a lot of the concentrations that you were starting with. You just have to know the salt concentration and your acid concentration. So it's just a quick and easy way to solve for pH or pOH of your buffer solutions, pOH if it's a base. So you can either do pKa plus the log of the salt over the acid, or the negative log of the Ka, which is what pKa is, right? Plus the log of the salt over the acid. And then if you're doing the base, it's salt over base. Okay? All right. So how do you solve for the pH of this? Do you use ice or Henderson-Hasselbalch? Ice, which we call the full equilibrium analysis method, and some things you have to use that, can be used under any condition. All right. The Henderson-Hasselbalch can be used when X is small, and you can use approximation. And so if Ka is small, so that is if it's 1,000 times less than your Ka, then you're pretty much okay to use it. And so most of the things we're going to be working with are going to be approximatable. Is that a word? You can use approximation for them. Okay, so in this particular problem, I'm going to work this one both ways, and I'm going to show you how it's easier with Henderson-Hasselbalch. I might call it HH. If I call it HH from now on, just know I'm talking about Henderson-Hasselbalch. It's a mouthful to say. All right, so it wants me to calculate the pH of a buffer solution that is 0.05 molar benzoic acid and 0.15 molar sodium benzoate, which is its salt. For benzoic acid, the Ka is 6.5 times 10 to the minus 5, okay? And so 6.5 times 10 to the minus 5 is small, so I can use approximation, even though these numbers are small, okay? And so to do this, I set up my ice table, the 0.05, the 0, and then my salt is 0.150 because these are buffers. That's always how you set up your little buffer ice tables. Okay, we don't know what the change is in the hydronium ion because we're trying to find the pH, so that's why we need the hydronium ion concentration. So we go down X in the reactants and up X in the products, and so we've got 0.050 minus X, and 0.150 minus X. And you might want to go through this ice table since you're still getting used to how to do that and how to practice it up. I will be using the approximation for this one. Okay, so after I've set up my ice table, I'm going to come over here, and I know that the Ka, which it gave me as 6.5 times 10 to the minus 5, so I don't have to look that one up, and that's going to be equal to the sodium salt or the benzoate, C2H5O2 minus. Remember, I can leave that sodium off because it's a spectator. Woo! Times the H3O plus, which is what I'm really interested in, and that's my unknown basically, divided by my acid, which is benzoic acid, which is a bigger acid. All right, so 6.5 times 10 to the minus 5 is equal to 0.150 times X divided by 0.050, and those of course are molar. So I'm going to cross multiply 6.5 times 10 to the minus 5 times 0.05 is equal to 0.150 times X. All right, and then I'm going to bring the 0.150 and divide. I know I'm doing all these steps, so some people that are a little rusty can follow me. Okay, and so that one should be pretty simple. X is going to be equal to 2.17, 17 times 10 to the minus 5 molar. And so we know that the pH, and that's what? The hydronium ion concentration, because that's X. And so the pH is equal to the negative log of X, or the negative log of 2.17 times 10 to the minus 5. And so the pH is going to be 4.66. So the only difference in the buffers when we're making them, okay, because we're making them, is that you're going to have some of your product starting out. So you already add some of your conjugate base or your salt into it so that it can go back and forth and it's going to resist those big shifts in pH. All right, now I did that one that way. Now the other way I told you I was going to show you is the Henderson-Hasselbalch way. And Henderson-Hasselbalch says that the pH is equal to the negative log of Ka, otherwise known as pKa, plus the log of the base, no, sorry, salt over the base, right? Am I right? Make sure. Yep, okay. All right, so salt over base. So the pH is equal to the negative log of 6.5 times 10 to the minus 5 plus the log of 0.150, okay, which is the sodium salt, divided by the base or the acid, whichever kind I'm doing. In this case it was an acid, so it's 0.050. That should say acid because I'm doing an acid one. It's the same formula regardless, but it's an acid, so I should write acid on there. All right. So when I do those numbers, what I'm going to get, you're going to get the pKa for this first number. So that's going to be 4.187. So if you look up the pKa for benzoic acid, it saves you a step, but we know how to do it, so it's not a big deal. And then the log of 0.150 divided by 0.050 is 0.477. This is a good place for a calculator check, making sure that your calculator is giving you the number that you want or that you should get. And so we get 4.66, and we got 4.66 the other way. Now, when this comes in handy is if you would have to balance the equation, because you have to balance the equation. You have to remember if it's 2x or 1x when it drops and all that. Henderson-Hasselbalch, you don't have to have a balanced equation for it. You just plug in the concentrations and look up the Ka and you're done. So what it helps with is you don't have to balance the equation and take into consideration if you're going down 2x or 1x or any of those things. Okay, so for these, if you can use approximation, if you want to use Henderson-Hasselbalch to work them, it's going to save you some time and effort. But remember, it's only for these, only for buffers, and it's only when an approximation is useful. Your practice one, notice your Ka is 4.9 times 10 to the minus 10. So that's definitely going to be usable. And when you, and I gave you the pKa this time, so super easy on you to do this one. So plug those in, see what you get, and you should be able to work this one out pretty easily. And I'll just tell you, let's see, you should get 9.14 pH. So I'll just go ahead and tell you what you should get, so that way when you work it, you'll know that you did it correctly. And again, you can do it either way. You can write a balanced chemical equation. This one's okay because it's 1 to 1 to 1. But if it's not 1 to 1 to 1, that's when you kind of get in a bind. So that is it. That's your introduction to Henderson-Hasselbalch and to calculating pHs of buffer solutions.